Hi, my name is Jianwei. In this video, I would like to present our paper 3D phase style transfer with a hybrid solution of NeRF and mesh rasterization. Let's begin with a bit introduction on our motivation. Given an input video around human face, we would like to train a stylized 3D face generator network such that at inference time, the user can input an arbitrary style image and viewpoint to generate a stylized normal view at that viewpoint. We would like the stylized normal view to be 3D consistent across different view angles, and having the style in the query style image, and also preserving the identity in the given user video. In other words, we would like to achieve 3D phase style transfer. Here are some visualization of our 3D phase style transfer results. The left two columns are input views, middle is the input style image, and the right two columns are stylized views. The stylized views not only capture the style from the style image and preserve the identity in the input. More importantly, they are quite 3D consistent across different views. In fact, the key differences between 3D phase style transfer and traditional 2D phase style transfer is the preservance of 3D consistency, which the 2D phase style transfer cannot guarantee to achieve. We propose a three-stage approach for this problem. The first stage is geometry training, where we train a NeRF network to reconstruct the 3D face in the given user video. The second stage is mesh optimization, where we start from the initial face mesh extracted from NeRF network with some background removal and texture refinement, and followed by an optimization process to transfer the style in the style image to the 3D face mesh. And finally, in the third stage, we extend the NeRF network to condition on style image and train it with multiple styles to further generalize. We use the stylized face mesh from the second stage as the supervision to train this generalized NeRF network. The main consideration for this three-stage setting is in compute efficiency. We only optimize for RGB loss at stage 1 and 3, where the NeRF models are involved, and only optimize for style transfer objectives in stage 2, where only the mesh representation is involved. This is because the RGB loss can be optimized with a randomly sampled pixel batch, while the style transfer losses need to be optimized with full images, which could be quite computationally expensive for NeRF. With this multi-stage training, which decouples the losses to different stages, we are able to train with high-resolution images within a couple of hours. Now let's take a deeper look into different stages. For the first stage, it is a standard 3D reconstruction problem, where we use a NeRF variant called News for better surface capturing and mesh extraction. For the second stage, we do mesh optimization. This is the main stage for style transfer. We use a differentiable rasterization to render images from a face mesh given a viewpoint, so that the gradients can be all the way back propagated to the mesh parameters. For style transfer, we would like to preserve the identity and only change the style. Therefore, throughout the optimization, we fix the vertex locations and only optimize for vertex colors. We first refine the initial mesh by inverse projection, which optimized for the RGB loss with the original input video frames. And then we remove the backgrounds with a foreground segmentation model. For style transfer, the loss objectives are similar to the ones in 2D style transfer without the identity loss, because we already fixed the vertex locations which preserve the identity. We use a pure data setting for the style transfer optimization, which we found quite significantly improved the style transfer quality. The main reason for that is that the raw style image often has a large head pose and identity difference, with the rendered face mesh images. Therefore, for each rendered face mesh image at random viewpoint, we use a 2D style transfer network to generate a stylized image that has similar identity and half-poles as the rendered image. We then use them as pure data for style transfer optimization. After optimization, we obtain a stylized face mesh. At the stage 3, we further extend the news model to be conditioned on style image. We design a hypernetwork whose input is the style embedding, and the output is the weight of the color network in news model. During training, we fix the weight of the SDF network to preserve the original identity, and we only optimize for hypernetwork and the color network. We train this network on a style image dataset of 200 images, and use the stylized mesh from the stage 2 as the pseudo ground truth generator for supervision. For each training iteration, we randomly sample a style and its corresponding stylized mesh, and a random viewpoint. We then render the stylized face mesh as the ground truth to train the hyper and color network with RGB losses. We compare our approach to 3 different approaches in the 3D scene style transfer. The compared approaches often only transfer the overall color tone of the style image and fail to capture the semantics of the face, while our approach can transfer the hairstyle, skin, and lip colors pretty well, and also preserve the 3D consistency across different viewpoints. We also compare our approach with these baseline approaches in terms of 3D consistency error and style transfer quality. Results show that our model outperformed the baseline by a large margin, especially in the 3D consistency error, where our approach is a magnitude better than the baseline approaches. Our approach can also enable style blending or style interpolation between 2 styles. In this image, we show some visualization of mixed styles from 2 style interpolation. Our approach can generate harmonious style from the style blending. Our model can also generalize to unseen style during training, because our model has been trained on multiple style images during training. So this is a visualization of an unseen style where our approach can generate reasonable style transfer result, even though the style image is not seen in the training. Finally, this is an ablation study for mesh optimization with or without peer data. On the left side, we show the mesh optimization result without peer data, where we directly use the render images from the mesh and the raw style images for the style transfer optimization. And on the right side, we show the ones with the peer data, where we use the peer data for mesh optimization. And without the peer data, the style transfer cannot converge well due to the large gap in the head pose and the identity. And thank you for watching the video.